I I am Ole Hill. I have been working at Civan Lasers in the European branch in Hanover for about 1.5 years as a project and welding engineer. In this time, I gained a lot of experience, especially on topics of die-cast welding and copper to aluminum welding. A lot of projects we handle in Hanover are on these topics. And yeah, today I would like to talk to you about some of the advantages that the Civan laser yields, especially for those applications, and where we've already shown some great welding results. Excuse me, I have a okay. All right. So without further ado, let's get straight into a topic that will address today, and that is the welding of aluminum die cast. As you see in the picture, these are cross sections of, let's say, historic welding attempts with a laser on aluminum
Oh,
die cast.
Ole, you have to reshare your
Yes.
screen. We don't see it.
Oh, I'm sorry. Yeah, then okay, you didn't really miss anything at the beginning. At the beginning, the first screen was just, is it working now? Um,
N not yet.
yeah, there we go. All right. Right. Now you see it, right?
Yes, this
Okay,
is
good.
good.
Okay, so yeah, let's go to the first slide. So here you see a few cross sections of aluminum die cast welding that was done previously of research groups or some other manufacturers of unknown origin. And what you see in die cast welding is typically a lot of porosity. And it's such a strong porosity that the welding is uh, not leak tight and also doesn't have a lot of strength because the pores can get so big that the interface is getting too small. So a lot of people have shied away from using laser welding for die casts, even though probably many of you are aware what the large advantages of laser welding are, which is accessibility, low heat input, and also in crazy welding speeds compared to stuff like friction stir welding, or if you compare it to a solution of gluing and screwing stuff together. So let me just go straight into some of the results that we could achieve with our laser and aluminum die cast. And as you can see on the left, you see a very, very flat surface of the weld seam. And on the right, or let's say in the middle, you can see a cross section and a longitudinal section, which shows very low porosity. There's still a measurable amount of porosity left, but it is strongly decreased from any other welding results we saw with the laser. And the strength of the weld is sufficient and it is also leak tight. So the very small porosity that you can still perceive in the weld does not seem to reduce the performance of the weld for many applications. And you also can see on the right the laser parameters, or at least the rough edge of the laser parameters, and you see we're welding at almost 10 meters per minute here. If you compare it to something like friction stir welding, you're on the magnitudes of 20, 30 times faster. But I will get into the details later in the talk. First, let me show you what the real dynamic beam shaping can look like on a high-speed camera. On the videos I will show you now, you can see a spiral, which is depicted on the lower right. And it is done in a way that the spiral is projected, or like each point of the spiral is projected after another. And then this results in a very dynamic melt pool. And you can even see it's like a circle from the inside to the outside, exactly like the spiral that we programmed for this weld. And these recordings are done with 300,000 frames per second, and the spiral is rotating at 5 kilohertz. And what you can see when the frequency, which we can tune, is dialed up all the way to 800 or almost 1 megahertz, you can see a static spiral being projected onto the workpiece. It is the same beam shape, the same material, the same laser parameters, just the frequency is on a way different regime. On the left side, it's like a very fast wobble, which you could not achieve with scanner mirrors at 5 kilohertz. And on the right, it is like um, maybe you know from some other manufacturers a static beam shape, which you do with a special mirror, for example. But in our case, you could do any kind of beam shape that you want, either as seen on the left in a very dynamic way, or as seen on the right in a, we call it quasi-static regime. Each of these regimes has different applications. For diecast, we actually use both. First, we do a weld, we call it the penetration weld, which goes all the way, well, as deep as we want in a butthole configuration, for example. And in the second pass, we go over the weld, over the piece and over the weld seam in a static way at 500 kilohertz, which smoothens out the surface in a very nice way. So let's just get shortly into how we do it with a Civan laser. So it is basically, um, maybe you have heard the term of it's like 32 lasers in one, and that is kind of true. We start off with a seed laser that is split up into 32 individual channels. And because they all originate from the same seed laser, they are in coherence with each other. And then these 32 channels are pumped up to the desired laser power that we want. For example, in the case of the laser in Hanover, we have up to 12 kilowatts of laser power. So each individual channel is pumped to something like 400 watts. And the phase of these channels can be tuned very precisely and also insanely fast in the megahertz range. Then these individual lasers, they are still coherent with each other. They are transported to our welding head with individual fibers, and then there they are arranged and focused on the focus spot, much like any other laser would be. But because they are in coherence with each other, they form interference patterns. And the position of the interference maximum can be tuned finely by changing the phase of the individual fibers. And what you see on the top right is basically the single point. If you would freeze during our laser process, you would see one of these individual spikes. And integrating over time is what yields these beam shapes that you know from all of our other videos and marketing material as well. Yeah, and this frequency can be tuned from low hertz regime even up to megahertz. Yeah, this has a big influence and is the core identity of our welding process. But it's important to note that at a single time point, it is just an interference pattern. It's not the entire shape. But if you go to something like 100, 500 kilohertz of refreshing rate, the material, let's say, feels the laser radiation as if it were a static projection. And this is all in goals to control the melt pool, tailor it to a specific application. Maybe you need more penetration depth in one part of your piece and higher on a different part. Or in the die-cast application, for example, we want first a very deep penetration, and then the second one, we just want a heat conduction welding. This is just a little bit of something to stir up your imagination of all the beam shapes that are possible. Basically, we have a tool where you can select individual points to create beam shapes, and note that all of these are actual videos taken in the focal plane and not just simulations. So all of these beam shapes you see on the right, were actually projected by our laser. Here's a different high-speed video I bring to you, also at a very high frequency, 240,000 frames per second. And this is once again a process which was done with the same basic laser parameters of power and feed rate, but two different beam shapes were chosen. And just to illustrate what influence this can have on the melt pool, you see a very, very large melt pool on the top, which can be beneficial for degassing, for example, yeah, to allow something that's trapped in the interface of the weld to escape to the top, like air or some kind of contamination. And then the bottom, it is a more narrow beam shape, and this will result in a more shallow weld seam and a deeper one. Other than it depends on the application, which one might be the right one. Going back to what I presented in the first slides, the die-cast welding. When looking at the literature, we see the idea, it is just a broad overview for you, that something has to be moving inside the weld seam. So these are all publications on laser welding of aluminum die-cast, and they all have in common that the weld pool is moved in some way. You see something like mechanically induced sound waves. You even see magnetic stirring, some special moving optics, but note that they don't get as fast as our laser does. Yeah, and some ultrasound magnetic waves, something like this, or moving the piece itself at very high frequencies. But all of these never got into mass production because they are too complex to adapt to a real workpiece. They might work in a laboratory, but yeah, overcoming the barrier to the market didn't succeed for these types of applications or these types of ways of inducing movement in the melt pool. But with the Civan laser, we could now do all of this, all of these great ideas that were here, and you see publications from the early 2000s. Yeah, but now we can finally do it in a really easy way with just a software interface, and the laser does the rest and does melt pool movement at a specific frequency that we want and in a specific shape that we want. Yeah, and this has led to these great results in aluminum die-cast. Here you see a few more cross sections and on the bottom two longitudinal sections. This was on LSE10MG, which is like, in our experience, a very common alloy for aluminum die-cast. But I can also tell you that it didn't matter at all which kind of alloy we tried. Like, we didn't see issues like hot cracks or residue, porosity, as long as let's say the alloy was casted in a decent way, and there are some things to keep in mind when casting for a laser process, then we could weld it in a very successful way. But I will come to these dependencies on the cast later in a comparison slide. Just a note that casting for laser welding is actually a good way of casting because you can avoid large, big walls, which are an issue for casting as well as welding. In this case, we achieved a 2 mm deep penetration, but we have done anything between 0.5 and 5 mm of penetration for aluminum die cast. And once again, in the velocity range of up to 10 meters per minute, sorry. What I am open to admit is that in aluminum die cast, you can always get an unexpected error which is caused by entrapped gases during the casting process. And if any of you have worked with aluminum die cast before, you know it is a very turbulent material. It has strong dependencies on the casting quality and also like local amassing of defects, let's say. If you take 100 pieces that are from the same machine, you will likely see defects happening more towards one specific region of the cast. But we have a solution for blowholes as well. And here in the upper picture, you see a weld seam that had a small series of blowholes, which resulted in this rough surface, and also a bit material got thrown away. But by doing a spot repair, we could close all of these holes. And on the right, you will now see a high-speed recording of this process as well. So this theory was to create a very, let's say, very large, it's just a few millimeters, but quite a large melt pool, which allows enough material that is basically next to the blowhole, melt all of this material and let it flow into the cavity that was created by the blowhole. And this process in the video looks quite long, but it is just over 0.2 seconds. So even if you get a few blowholes in one weld seam, it is a very fast repair. And as I mentioned previously, we then do a second pass over the weld seam anyways, which also smoothens out the repair. So it can be done in a way where it's not visible afterwards. Well, this good question I hear coming from your mind, but how do you know where to repair? Where's the blowhole? And we incorporated a sensor for that. It collects data from the focal spot. It is basically collecting all the radiation that is happening during the laser process, and you detect the peak that's happening caused by a blowhole, and you know, well, basically you take the timing of the start of the process until this event occurred, and because you know the trajectory that you welded with your scanner, you also know the position of this error. So in that way, you take the data, you analyze it, of course, automatically. You go to the desired spot and apply your spot repair. On the bottom left, you can see a comparison like two completely different die-cast materials. The one on the left seems to have a bit more residue porosity compared to the one more towards the center. What I would like to point your eye to is in the one towards the middle that has the 1.6 millimeters of penetration depth. You can see not one weld, but a second pass, and that is the polishing pass we call it the polishing pass. This is a second pass done at a very high frequency where we intentionally don't create a keyhole. We just remelt the surface to make it very flat, and you can see it in this etching as well. It's just a small, let's say, half moon in the top 0.3 millimeters. Yeah, just to reduce the surface porosity and also make it less likely for any pores to cause a leakage, let's say. And it also results in this very nice looking surface finish, which is like a little bit shiny and also has these repetitive patterns that you might recognize from manual welding. On the right-hand side, you see the same part, but in the middle it had a few sections of overlap. There we use a different kind of beam shape, one that has more, let's say, a more centered energy to go deeper inside the underlying material. We didn't need a wide weld seam. On the left side for the butt weld, we intentionally go a bit wider to cover up any gaps that might appear. But for overlap, you don't need to cover gaps in the X direction, more covering gaps in the Z direction. Yeah, and what you see is the cover image of an overlap of a die-cast cover into a die-cast chassis. What you see here is a different kind of configuration. And there we welded a die-cast chassis and used a wrought alloy cover. Depending on your application, that if it is a valid choice, it makes manufacturing a lot cheaper because, well, now you only have one die-cast part and not two. And also manufacturing the covers is a lot cheaper. at least in our experience, we only see advantages of going with a rod alloy as a cover if your design allows it. The weld quality is even higher. Basically, let's say you now only have 50% of the dangerous material of diecast, and you have 50% of easier to weld rod alloy. As you see on the left, there's basically zero porosity inside this weld. And on the right, you can see overlap of rod alloy over diecast. That seems to be the most challenging weld, but we have a way of getting a nice wide interface as well. It's important to note that the clamping is kind of an important task when you weld overlap. Um, I think that's regardless if you're using a Civan laser or not. If you want to weld successfully in overlap, you need a good jig. Here I brought to you a video from our lab in Hanover. I'm just going to let it play. It's welding in real speed, so you get an impression of what 150 millimeters per second can mean on a workpiece. And it's like, yeah, the size of a normal notebook, for example. And yeah, now here you see a close-up video as well of the weld seam. This is done with 2 passes and to get this nice surface finish. And this is the example I told you about. Instead of using a casted cover, you use a rod alloy. Yeah, that makes it a lot cheaper. I'm just going to play the important parts again. I wanted to show here the overlap part in the middle, as you see. And then we had to remove the clamping to not burn it for the last internal line. Yeah. And then the way all around. Okay. So to sum up this topic of aluminum die-cast welding with a Civan laser, where I bring up a comparison to a competitive welding welding technique that is friction stir welding. If you're not familiar with it, you basically use a pin, you apply a lot of force, and you work below the melting temperature. You basically, I'm lacking the English word, sorry. But you're just mixing the two joining partners. You're not really melting them. And this has, to be fair, an advantage of not exploding any residue gas that is inside because it is relatively cold at something like 300 degrees or 400 degrees. But it is very slow and you need to apply a lot of force on the workpiece. And also the pin itself is subject to wear and tear, so you need to keep replacing the pin every roughly 1,000 meters of welding, and you also have a deteriorating welding quality over this period as well. If your tool is getting less sharp, let's say, of course you need to watch out for defects. Really an advantage, or like disadvantage is that you need to these high forces, so you are limited to kind of bigger parts. You cannot weld like a small box like this that you need for a control unit, for example. And you also have limits of accessibility. The weld seam has to be exposed. You cannot have it directly next to, let's say it cannot be 3D to keep it simple. And well, the laser welding has some advantages compared to, or I guess a lot of advantages compared to the friction stir welding. And one of this is that the laser is, let's say, always sharp. You don't have any wear and tear on the laser at all. So you can rely on it to work the same as yesterday and last week and last month, as long as you have control over the rest of the system, the laser will perform in the same predictable way. Well, as I mentioned, it's magnitudes faster, and also no direct forces are applied to the part, only forces indirectly by cooling gradients. But you have those with any kind of welding. So I wouldn't say that's specific to laser welding. The overall heat that you input is also smaller because the process is so much faster and you only melt the real specific part of the piece that you want to melt. Yeah, and I always say like you can weld anything that you can see by eye. There are not a lot of spherical restrictions for the welding. The Civan laser works in the setup in Hanover with a 1.5 meter effective focal length, which results in something like 1.1 meters of distance between the exit window and the workpiece. And this, yeah, you don't have a large processing head like other laser processes, which is very close to the workpiece. We are very far, and so I say everything that you can see by eye, the laser can also reach. Going to a kind of related topic is an example of an aluminum plate cooler. In this case, it is aluminum 5754 series, and this is a cooler that we designed ourselves for just as an example of what you can do. So we don't have it under any NDA because we ourselves ordered these plates. So here we can reach real high speeds, like 30 meters per minute. It's like 3 times faster than what I showed you before. And this is an overlap configuration of 1 millimeter over 2 millimeter. We found that to be quite the common application in aluminum cooling plates. And the beam shape that we use there is kind of elongated to the sides with the goal of enlarging the interface between the upper and the lower plate. I'm going to just play the video on the bottom right again. It's a high-speed video, high-speed recording. Well, it's not on a high magnification, but I think it's good to get an impression. And this is now like a real speed video. So you can see how fast it is going. And this piece is like 35 centimeters from left to right. Left you see a cross section, and on the lower part you see a longitudinal section of this workpiece. Another topic important to automotive industry is welding of copper. And if you tried copper welding with a laser, you will be familiar with the problem of very high reflectivity of copper. And that's why some solutions include green or blue wavelength, which has a higher absorption rate in the copper. And even doing something like 2 lasers, one in the blue or green regime to create a keyhole, and then a laser in the infrared regime, like the Civan laser, to keep the keyhole open. And you do that because you have typically a better beam quality and also lower cost per kilowatt in the infrared regime. But synchronizing 2 lasers is, as you can imagine, not that simple. And we kind of have a similar idea when welding copper. So we first do a very concentrated beam shape, which has really high intensity on a single spot. And after first millimeter of welding, we switch to a different beam shape. Because, I'm sorry, I forgot to mention, this reflectivity issue is really only true for solid copper. Once the copper is in a liquid form, the absorption rate in the infrared increases by a few magnitudes. So it's only really overcoming the solid mirror-like copper surface. So we use a very concentrated beam shape for the first millimeter to create a molten copper and a small keyhole. And then we switch to a bigger beam shape, which creates a more stable keyhole. And that allows us to do different kind of copper welding setups. We have even done fun things like doing an overlap of 3 millimeter over 1 millimeter. So that's quite the challenge to melt exactly 3.5 millimeters in copper, a material with such high heat conductivity. And the picture on the right shows a setup of 1 millimeter over 2 of copper and also a nicely edged welding seam. And on this picture, you can see much thicker copper that was 4.6 millimeters with the surface and the bottom and a nicely shaped root. And at a feed rate of 40 something millimeters per second, it's a very competitive welding speed and very nice weld quality. And finally coming, I think, to the crown jewel of welding, which is dissimilar materials. And of course, we also try this topic out because I always say like this Civan laser is showing its strength where other lasers have their limits, their boundaries. So in this case, it is copper to aluminum, and yeah, also if you have tried it, it's usually very brittle. Sometimes you cannot even test for material for some material properties because the samples already fall apart when you take them out of the jig. So this is yeah, this is the real challenge of aluminum to copper welding. And well, on the top right, you can see the surface picture of a small weld between aluminum and copper. And yeah, what is nice to see is that the weld itself is looking almost exclusively like aluminum. And our experience, once you see some bronze in the weld seam, you know it's going to be very, very brittle, and you have molten too much copper into the mix, and then you get intermetallic compounds, which are very brittle. So the goal is to melt as little copper as possible. But you want to avoid a situation where it's only brazing. We have seen this as well. We are looking at the piece and thinking, oh, this is nice. You have a weld seam that is like very silver. You didn't melt too much copper, but then you break it apart and you see that you really didn't melt any copper at all. You just brazed the aluminum to the copper. And this results in insufficient mechanical strength and also not that nice of a um, electrical conductivity. Yeah, so we had a very successful run with using a quite narrow beam shape, a small spiral, and yeah, we manipulated the workpiece in a way that we could get this basically vertical weld seam on the left side, which you see in the cross section, and the angled weld into the aluminum, which doesn't matter because you can melt as much as aluminum as you want. It's maybe hard to see in this picture, but this is most of the interface in the copper is very slightly molten. It is not the case that I described before, which is a brazing of aluminum. And just a few micrometers of copper are molten, and this results in a weld that is not so brittle. It will never have the strength of a copper to copper weld or aluminum to aluminum weld. I would be very surprised to see that happening. But our results, let's say, you cannot break it apart by hand. I will also have a nice video showing you that it is indeed quite durable. And what we could measure recently was excellent conductivity. So we had compared the conductivity of pure copper, of pure aluminum, and then the same width over our welding seam. And the conductivity resulted in basically, let's say, the weld didn't matter. We had the conductivity of copper and aluminum. If you add them up and divide them by 2, this was the conductivity that we achieved when measuring over the weld seam. So we are very excited to get this result. And I can also show you one of the pieces. So these are 50 by 50 millimeters coupons. So not that large, but if you want to get through a lot of different samples, you don't want to weld meters and waste a lot of material. And in this video, you will see the front side and also the back side of the weld. And you will also now see it being thrown from roughly 1 meter. and it didn't break. So um, yeah, this shows like we are in the process of doing coupons for real mechanical testing, but this is as much as I can show you in this moment. So it did survive being thrown from 1 meter in height. We also, yeah, we don't sell just the naked laser. We want to make it, as everyone says, a turnkey solution. And this example right here from a laser integrator, system integrator from Germany would be a solution with a turntable where you can insert parts on one side. It's turning behind the laser safe wall. And then the parts are welded. In the meantime, you swap out the welded parts for new ones, and then you repeat the cycle, including our laser in combination with a scanner. And well, this is a lot of details. If you want, I can send you all the details afterwards. But yeah, just as a short notice, it is like a 4x4 or 2x3, sorry, footprinted cell where you can weld, for example, aluminum die cast in the way I've shown you today. Yeah, and everything that you would wish for, like the 4D sensor, automated jig control, automated rotation, part detection, and all of this stuff. Just a short overview of other applications that we have. We're not limited to just aluminum die cast and aluminum and copper. It's also applications of very, very deep penetration with our lasers that have up to 120 kilowatts of optical power. There you can see an experiment done to go in a single pass over 70 millimeter in a butt weld configuration. And also thick aluminum welding. On the bottom left, you see 15 millimeters of aluminum welded. Yeah, and some of the other examples that I showed you as well of die cast to different kind of alloys. I would like to close this presentation with an invitation to us in Hanover. We call it the Dynamic Beam Laser Workshop, and this will be the first time we host an event like this, and I'm very excited about the positive response that I got from the scientific community. I reached out to them last winter and said we would like to get in touch, keep the relationship close, allow for a very deep discussions between the experts and also between our team as well. And so we have, I think it's now 8 or 9 scientific talks and also a lab tour in Hanover on June 11th. And if you would like to join, you can just hit me up with an email. I will also post the registration link in the chat in a few moments. Yeah, with that, like once again, an invitation to Hanover, not only to this DBL workshop, you can also come visit us if you have a specific application in mind and you want to see how our laser performs on it. I'm just going to go ahead and say that we do typically 2 days of experiments without charging you. And if you want to, yeah, come check it out. Don't hesitate, and then we can see if we have any slots open in our laboratory. And also now I'm very welcome to receive questions from you if you want to know more about a specific topic or something else I didn't touch on yet.